All right, hope everybody had a good fall break. Here we are, lesson 2 of Unit 4. This one's about parallelograms. Now, today's lesson has to do with two sections out of the book, 6.2 and 6.3. And 6.2 and 6.3 are pretty much converses of each other. 6.2 and 6.3 use a lot of the same diagrams, and they're all about parallelograms. 6.2 is the one that says stuff like this. I'll go back to that header in a second. That if it's a parallelogram, then you know all this funky stuff is true. And the stuff in 6.3 is kind of the other one, the other way. It says if you know certain things about a quadrilateral, then it's a parallelogram. But like lots of things we've done already this year, what we're going to end up doing for you to make life easier is to call those things a biconditional. So a lot of these biconditionals will have one theorem number that's from section 6.2 and another theorem number that's from section 6.3, and they have to do with one property of parallelograms. But we're going to let you use it both ways. We're going to let you use it as, well, if I know it's a parallelogram, then I know this stuff is true about it, and if I know this stuff is true about it, then I know it's a parallelogram. Hopefully that makes sense. Rewind and watch that a few more times if not. Okay. So first of all, what's a parallelogram? Parallelogram by definition is that it's got this going on, that both sets of opposite sides are parallel, which is great because that's part of the name. They use this symbol right before the letters to signify that's a parallelogram. I think that's kind of a flimsy way to use a definition. They just put this little symbol here, and you're supposed to remember that, hey, that means it's a parallelogram. Hopefully you get used to that, and here you see it right here in context. All right, so here's some of these properties. There's 4 or 5 of them depending on which way you are going in the biconditional, but they get pretty easy to remember. The first one is this. If you get a parallelogram, then both sets of opposite sides have to be congruent. So JM and KL are congruent, and ML and JK are congruent. So again, that's going to end up being a biconditional. If you knew those opposite sides are congruent, then it's a parallelogram. And here it's saying if it's a parallelogram, then you know opposite sides are congruent. So those things go hand in hand. Only works with quadrilaterals, doesn't work with hexagons or anything funky like that, but if the opposite sides are congruent, then you know they also happen to be parallel. This is pretty easy to prove with congruent triangles if we split it along here with a diagonal. I can show you that in class, but it's not something I'm going to ask you to prove. I'm just going to ask you to internalize and remember and cite this property of parallelogram about opposite sides congruent. The other one is opposite angles being congruent. If opposite angles in a quadrilateral are congruent, we know it's a parallelogram, and if it's a parallelogram, we know opposite angles are congruent. Just kind of easy to pair up with this one. So that's nice. Next one, consecutive angles are supplementary. I think this one's a little bit easier to see. You remember from when we did parallel lines and transversals a couple of units ago that we had this thing called same side interior or consecutive interior angles. If you have parallels here and here, then you know these angles are supplementary. Well, that's exactly what's going on here. We have supplementary angles that are between parallels. And since this set, JK is parallel to LM, that makes X and Y supplementary. But look at JM parallel to KL, that makes this X and this Y supplementary. So we could just kind of dance all the way around the parallelogram, and every time we have a pair of angles, we're going to have that. We're going to have one of these systems going on. So it turns out every consecutive neighbor is supplementary. That's nice for figuring out angles in parallelograms. If you know this is a parallelogram and you know one angle, you can get the rest of the angles really quick. So say I know this is 110 degrees. Well, I know its neighbor has to be supplementary with it, so that makes this have to be 70, and it makes this one have to be 70. Oh, and by the way, opposite angles are congruent. Okay, or I could use the supplementary rule and go this way and say what's supplementary 70, 110. So we know that has to happen pretty quick. So by the same token, if it has one right angle, well then that has to be a right angle because they have to be supplementary. Oh, and opposite angles are congruent, so that's a right angle, and there's 360 in a quadrilateral, so that has to be 90. So if you determine that there's one right angle in a parallelogram, which is really popular thing to happen on coordinates, you don't have to prove all 4. You can stop at 1 because you know if it has 1, that's what this property is saying. If it has 1, it has to have all 4 as a combination of these other properties. Okay. There's a couple more. They have to do with the diagonals of a parallelogram. If you draw a parallelogram and draw the 2 diagonals in, the diagonals meet at each other's midpoint. So the point where they meet here is called P. P is a midpoint of BD, and P is a midpoint of AC. So PC and AP are congruent, BP and PD are congruent. Very handy. And this one, not as handy as you might think, but as soon as you draw one diagonal of a parallelogram, it forces these two triangles to be congruent. And I think you could see that pretty quickly by side, side, side. We already knew in a parallelogram that that was congruent to that, and that was congruent to that, and of course this thing's congruent to itself, so no big surprise here. We're going to have congruent triangles. Okay, so here's all those things written out as biconditionals as you will use on the test. Through 6, 4, and 6, I think he meant 6 something else, 11. So opposite sides, opposite angles, and the diagonals being intersecting at the midpoint. So if and only if means we can use these both directions. If it's a parallelogram, then blah, and if blah, like if all these properties are true, then it's a parallelogram. And so you just have to keep track of, are we talking about sides, angles, or diagonals? Actually, not that hard to keep that stuff straight. There's one more way. Now, this one doesn't work both ways. This one only works that if you know it's true, then it's a parallelogram. This actually just wouldn't be useful the other direction because it's part of other ones. So this is kind of a shortcut way to get it to be a parallelogram if you're trying to prove something's a parallelogram. And we are going to have lots of proofs where the proves section says prove it's a parallelogram. And this is just about one pair. If you know one pair of opposite sides is both parallel and congruent, it forces a thing to be a parallelogram. The last way you could prove something's a parallelogram would be by the definition. Don't forget about that. If you had some proof and the proof was asking you to prove this is a parallelogram, and you're able to prove this, and you're able to prove this, then guess what? You've proven it's a parallelogram by the definition. And that's not out of the question, because you might be able to prove those things are parallel by AIA or CIA or corresponding or all kinds of other things. Slopes show parallel, so those are all valid ways. Okay, so here's some actual problems. Find x, y, and z. Okay, so we have all these properties. Opposite sides are congruent, opposite angles are congruent, diagonals bisect each other. Let's see what we can do here. All right, BD is supposed to be 42, and BCD is supposed to be 63. Oh, BCD, this whole thing is 63. Okay, if that's 63, then I know this whole thing is 63. Let's just write that out then. 39 plus 4y plus 5 is 63 because opposite angles are congruent. So doing some algebra magic, I can solve that. Yeah, that turns out to be a yucky one. Other thing we know in a parallelogram is that opposite sides are congruent. So there's the first thing. I also know that this 2x plus 13 and this 3x plus 4 have to be the same, so I can say that. The opposite sides are congruent. So that's not so bad. Oh, and then, so I guess I didn't need this. 4x minus 1 had to equal this thing down here. That wasn't very, I don't know what that is, so that wasn't helpful. BD is 42. Oh, okay. If BD is 42, how does that help us? Well, if BD is 42, I know that each part of this here has to be 21 because F is a midpoint because the diagonals hit each other at midpoint. So 21 is another way to say 2z plus 4. So that's how I'm going to find z. 2z plus 4 equals 21. I'll just crank this one out. 2z, whoa, z is 17. Another fractiony one, z is 8.5. All right. Solve this one. Again, we have a parallelogram. So I know that diagonals bisect each other. It looks like we have a system here. I know these are the same, and I know these are the same. This is going to be a bit yucky because I have x and y in it, but then it'll be calculator time. So let me write this out. All right, I had to get that thing out of the way for a second, and then I'll just enter this in the calculator. And to enter this in the calculator, I have to enter this as a system, remember. 2y plus 2 equals 2x plus 6. Okay, I go menu. Oh, you can't really see this. I go, whoa, wrong thing. Just a second. Can I grab this? Yeah, okay. So it was 2, and enter system. Menu, algebra, solve a system. Sure. 2y plus 2 equals, now I forgot what I had, equals 2x plus 6. And, whoa, how'd that happen? X plus y equals 17 minus x. X plus y equals 17 minus x, and it's all set up for me. I just do that, and boom, x is 5 and y is 7. Okay, that's nice. Some people on the test forgot about this. This is a calculator job. You can do it by hand, but it's no picnic. Just stick that in the calculator and that pops out. And why not? All right, we got a proof. Let me copy the given. Yeah, it's hard for me to write in the middle of the screen here while I'm paused. Okay. Oh, well, great. If we're given that these are parallelograms, we're in great shape because we just learned like 5 or 6 or 8 properties that we know for sure just from that. Opposite sides are congruent, opposite angles are congruent, opposite sides are parallel, diagonals bisect each other. There's so much stuff here. But what I'm concerned with probably has to do with angle B and angle F. So if I can say anything about angle B or angle F from this, that would be good. And the first thing I can think of is, well, opposite angles in a parallelogram are congruent. So let's say that. Angle B is congruent to, and I can just say angle D, there's only one angle there. I'll just say opposite angles in parallelogram. There's a number for that biconditional, but that's easier than looking at that. Also, D is congruent to F because of the little parallelogram. So same reason, I'm not even going to make a different step numbers. This is still part of step 2. D is congruent to F, still part of step 2. Well, if B is congruent to D and D is congruent to F, this is a textbook example of when to use the transitive property, which we didn't actually see much last unit. But thing 1 is congruent to thing 2 here, and thing 2 is congruent to thing 3. Therefore, thing 1 is congruent to thing 3. All right, I got about 4 minutes. See if I can get this. Oh, yeah, these are the ones you know I love to hate. All right, so it's coordinates with variables. We know they have to be parallel. We know that opposite sides have to be congruent and that sort of thing. Okay, this is 0b. This has to go some certain amount down this direction and have the same height at b. Okay, that's great. How long is this horizontally? Well, it goes from here to here. It's got to be the same length, like this and this. This goes from a to 2a plus 2. How much does that add on in the x direction? It adds on another a and it adds on 2. So this has to be a plus 2, which is weird. And the height of this thing, you know, the height is always constant because these are parallel. This went from a height of b to a height of b plus 4. This has to have the same height up here at b plus 4. Kind of a strange little deal. Show the diagonals bisect each other. Okay, we need to find, does that bisect this and vice versa? The best way to do that in coordinates is to try to find the midpoint of both things and see if it actually has the same coordinate. So we're going to find the midpoint of PR, and that equals a plus 2 divided by 2 as an x-coordinate, and b plus 4 plus b divided by 2 as the y-coordinate. And over here we're also going to find the midpoint of QS. And the midpoint of QS is 0 plus 2a plus 2 over 2. I'll just write that as 2a plus 2 over 2. And the y-coordinate is b plus 4 over 2. Wow, that looks familiar. Can you see these are the same? 2a plus 2 over 2 and 2b plus 4 over 2, they are going to be equal. I don't really want to simplify that. I can already tell they're going to be the same. All right, last 4 problems. Is this a parallelogram or not? Well, opposite sides are congruent, so that's enough. Great. Next. Okay, opposite angles here are congruent, but I don't know about this one and this one. It'd be really nice if they were both 110, but it could be that one of them is 100 and one of them is 120. So I don't really know. These 2 angles being congruent does not force the other 2 to have to be congruent. I can tell what they're going to add up to, but I don't know what they are separately. This one's really going to frustrate you. Yes, this is congruent to itself. AIA angles here force these to be congruent. What else can I possibly say? Between the 2 triangles, I just have side-side angles, so that's no fun. I've even got some parallels here, but there's no other angles I can say are congruent. This is actually a frustrating one, and it turns out to be no. If you want to argue this one in class, be my guest, but there's really no way to tell. This could be a trapezoid. I'd be stuck. And the very last one, I have a luxurious amount of time left. All right, so those are parallel. There's a theorem that said if a line is perpendicular to one of a set of parallels, it has to be perpendicular to the other. Or think of this as CIA. I know I have supplementary angles here between parallels. I also do over here too. I got 4 right angles, so guess what? This is a rectangle, folks. And rectangles are parallelograms. Also, because these are parallel because I've got one line that's perpendicular to 2 parallels and another one that's also perpendicular to those 2 parallels. Or look at the CIA angles here and here. There's lots of ways to say that. I would say this is a parallelogram by the definition of parallelogram. Okay, We made it. See you in class.